Today we're going to work on something called accumulation functions. This notation right up here, this is notation for a definite integral. And definite integrals are one of those things we're going to be working with for the rest of the year. And at its core, what it is, it's a way to represent the area between a function and the x-axis, where x is between a and b. So visually what this looks like, here we have the integral from 1 to 3. So on our graph, we look at the x-axis, and we look at 1 and 3, and we look in between them, and we look at the area underneath the graph until it gets to the x-axis. So this is kind of a rectangular shape with a curved top, and whatever the area of this shape is, it looks like this shape is about 7 or 8. That would be the definite integral. So it's a way to represent this area right here. Now, sometimes you have area above and below the axis. So for here, if we go from -1 to 5, at first the graph is underneath the x-axis, and then it crosses over and it goes above. So we're going to distinguish these two areas. If it's below the axis, it's going to be negative. Above the axis is going to be positive. So we scroll down here, area that is below the x-axis is negative, and above the x-axis is counted as positive. So here for this definite integral, we have 3 different shapes. We have one below, one above, one below. The definite integral represents the areas added together, but the areas underneath are negative. So for the first one here, we have the integral from 1 to 3 of f of x. So we look at our graph, let's get to the drawing, and we're looking between 1 and 3. So left and right, this is the spot we're looking at. You can see we have a triangle that's above the axis and a triangle that's below the axis. So we want to find the area of both of them. So above the axis, this just goes back to geometry. The area of a triangle is 1/2 base times height. So this green triangle has a height of 3 and its base is 1. So its area is 1/2 times 1 times 3, which is 3/2. Now the red triangle is the same thing. Its height is 3, its base is 1. So its area is 1/2 times 1 times 3. And then because it's below the axis, we count it as negative. So altogether, the integral is going to be 3/2 plus -3/2, which gets us 0 for our final answer. And it's worth pointing out another way you can think about the area being negative is the height of this red triangle here is really -3 because it's down 3. So area below the axis is negative because the height is going to be negative. All right, for number 4, the integral from -5 to 7. That's going to go from here all the way to here. So we're going to have a couple different shapes here. We have this little spot above the circle and below the axis, and kind of gets to the top. And then we have a triangle, and then we have a triangle that's above the axis that I'll shade in green. So we have 3 different shapes. First things first, if you notice these 2 triangles have the same dimensions. The green one is 3 by 3. So that area is going to be 3 times 3, which is 9, divided by 2, which is 9/2. And this triangle right here is 3 by 3 as well, meaning it's going to be -1/2. So those are going to cancel out with each other. So for this question, we really want to figure out just what is this area here above the circle and below the axis. So the way to do this is to think of it as a rectangle where you're cutting out a half of a circle. So the rectangle has a width of 6 and a height of 3. So the area of the rectangle is 18. And then we could chop out the area of the circle, where from the center to the edge, it has a radius of 3. So it's going to be pi r squared, but because it's a half a circle, it's 1/2 times pi r squared. So this is going to come out to 9/2 pi. So our final answer is going to be 18 minus that half circle, minus 9 pi over 2. The triangles cancel out, so we don't have to worry about those. But this is going to be the total area. Now, how is this useful? Well, the area under a curve is particularly useful when you're looking at the rate of something over a period of time. Let's imagine you're graphing something that's miles per hour on the y-axis and just hours on the x-axis. Well, if you imagine calculating the area, to figure out the units, it's actually going to be the y-axis times the x-axis if you're calculating the area. So when you multiply the rate by the time cancels out, and you just get, in this case, the miles. You just get the top unit. So the integrals are helpful because they turn rates into fixed units. So here, what I was just saying here, the unit for the area under the curve is always the product of the y-axis and the x-axis, the units of the y-axis and the x-axis. So if you graph miles per hour over a period of time, the resulting area is going to be miles per hour times hours, which is miles. So here you're going to road trip and travel at a constant speed of 65 miles per hour. So that graph is just going to be a horizontal line. Your speed's not changing. Your speed's always 65. And you do it for 5 hours. So the shape you end up getting is a rectangle that's 65 by 5. So 65 miles per hour times 5 hours. When you multiply those together, that's going to get you 325 miles. Now, some of you might be thinking, oh, couldn't we just do distance equals rate times time? And you could. In this case, that would get you this answer much easier. But integrals are helpful because your speed isn't actually going to be constant. When you actually drive, what the graph's going to look like is something like this. Your speed's going to be going up and down. So if you want to find the total distance and be precise with it, the exact area here is going to get you your total distance. So as the year goes on, we're going to work for ways to calculate this exact area. But for now, we're just going to be dealing with simple shapes. So let's look at a problem that's a little bit more complex to kind of show you what I mean. So here, we travel for 10 meters per second for 20 seconds. Okay, a lot going on here. I'm going to draw a graph. Meters per seconds are units. We're going to put that on the y-axis. Time is seconds. We're going to put that on the x-axis. We start by going 10 meters per second, and we do that for 20 seconds. So we start off with a horizontal line before spending 10 seconds speeding up to 30 meters per second. So now we're going to go up at a constant rate to 30 meters per second. And this whole thing took 10 seconds. So that's going to be at 30 seconds. 20 plus 10 gets us 30. I'm going to erase this unit here just because it's interfering with the time. So we travel 10 meters per second for 20 seconds before spending the next 10 seconds speeding up to 30 meters per second, where we travel for the next 60 seconds. So we travel until we get to 90. 30 plus 60 gets us 90, and we stay constant. After which you then steadily decrease your speed to a stop for the next 20 seconds. So we're going to assume that's linear. We go from here, and we go down until we stop at 110. So it's not drawn to scale, but this is essentially what this problem said. We start off by going slow, then we speed up, then we come to a stop. So if we want to calculate our total distance, this is going to be an area problem. So I'm going to split this up. I'm just going to do a rectangle here. First, we travel 10 meters per second for 20 seconds. 10 times 20, that's going to get us 200. Now for the next interval, I'm actually going to break this up. So we have a rectangle on the bottom. This rectangle is a height of 10 and a width of 10, giving an area of 100. And then on top of that, we have a triangle. For this triangle, the height is 20. 10 to 30 is 20. And its width is 10. So 10 times 20 divided by 2, because it's this triangle, gets us 100. So in this first 30 seconds here, we traveled 400 meters. Let's keep moving forward. Now the purple's nice. We can just do a rectangle. 30 units high, 60 units wide. 30 times 60 gets us 1,800. And now finally we're coming to a stop. So now this is just going to be a triangle with a height of 30 and a width of 20. 30 times 20 is 600. Divided by 2 gets us 300. So our total distance over this time could get by adding all of these areas together. 200 plus 100 plus 100 plus 1,800 plus 300. 2, 3, 4, 22, 25. That will give us a total distance of 2,500 meters. Okay, the last type of problem we're going to work with today. A tub with a leak is being filled with water. So we have a tub. It might have some water in it, but water is going in, and as it leaks, the water is also going out of it. And what this graph here represents, the graph below represents the net rate at which water is entering the tub in gallons per minute. So we have gallons per minute and minutes. So if we want to figure out how many gallons are being added, it's just the area under the curve. It tells us there was 200 gallons to begin with. So we start with 200, and that's going to change. It might get bigger, it might get smaller. The change is the area under the curve. That's the big takeaway from today. When you graph a rate on the y-axis and a time on the x-axis, the area under the curve tells you how much change has been accumulated. So to figure this out, we're going to break this up into shapes. I'm going to draw a rectangle here below the circle. And now when we get under the axis, now we have a triangle and a rectangle. So we have 5 shapes here to worry about. So shape number 1 is just a rectangle. 3 times 2 is just 6. That's easy enough. Now we have a quarter circle here. The radius is 1, 2, 3. So the total area of the circle will be 9 pi, but it's a quarter of a circle, so it's only 9 pi over 4. Area number 3 is 2 by 2. So 2 times 2 is 4, divided by 2 is 2. Now, shape number 4 is below the axis. So I'm going to make this red just so we don't forget. It's 2 by 2. 2 times 2 divided by 2 is -2. And this last shape here is a width of 3 and a height of 2. So that's going to be -6. So if we add all of these together, the net change, plus 6, plus 9 pi over 4, plus 2, minus 2, minus 6. Well, a couple of things are going to cancel out here. So the total net change is just going to be 200 plus 9 pi over 4. But it also asks, when was the amount of water in the tub at a maximum? So to figure out when it's at a maximum, you kind of have to think about this one a bit. It starts by having things get added to the tub. The net change is positive, but once we get to 5 seconds, now the net change is negative. So water was going in, and then it started going out. So right here at 5 seconds, something changes. So the maximum is going to be the first 3 shapes added together before we start taking the water away. So if we do that, it's going to become 200 plus 9 pi over 4 plus 8, which is 208 plus 9 pi over 4.